Hello everyone, and welcome to this talk about real-time simulation for audio applications. My name is André Plätze and I'm streaming from Berlin, capital of Germany. A bit about my background: I have a master degree in computer science with physics as a secondary subject. I work in research, and in my spare time, I develop open source software, which is the reason for this talk. I play the electric guitar since January 2018, and I'm pretty much interested in audio engineering in general. The project I want to talk about tonight is known under the name GoDSP Guitar. It's available on GitHub. You can see the address here. And it's described as a cross-platform multi-channel, multi-effects processor for electric guitars and other instruments. That's also the project description on GitHub. The project started on October 1st, 2013, and we had our first stable release, version 1.0.0, on December 17, 2018, so a bit more than 5 years after the project started. The first time I got invited to all the talk about the project was on November 20, 2019, so not quite a year after our first stable release. And the current release of the software is version 1.7.0, which was released on August 28, 2022. As mentioned on this slide, the software is used by hobbyists and professionals from all over the world. And these are some countries where there are users from which I got feedback. But the list is probably not complete, since most users of open source software will never interact with the project developing the software they use. This is how our source code management system has been accessed over time. These are cumulative accesses, and the dark blue area in this diagram represents full clones, which is the standard operation in Git when you newly access a repository, while the light blue area represents accesses to subsets of the repository like individual files, branches, etc. And as you can see, in the end of August 2022, we have surpassed 50,000 accesses to our source code management system. Now, we don't know how many users our software actually has, but judging from this data, there appears to be quite a substantial user base and quite some interest in the software in general. An interesting thing to note when you look at this diagram, and remember I held my first talk about this project in November 2019, which is here. An interesting thing to note is that the full clones start increasing at the second half of March 2020, which was when most of Europe went into lockdown due to the first wave of the COVID-19 pandemic. Then, at least in Germany, but I assume it was similar in other European countries as well, in the first half of May 2020, restrictions eased, and you can see that the number of full clones per day goes down again. Then, in October 2020, at least in Germany, restrictions were tightened again, and interestingly, we don't see an immediate rise in full clones, but towards the end of 2020, the alpha variant arrives, and then full clones really took off and basically haven't stopped doing so. Now, obviously, correlation is not causality. However, one might speculate if perhaps, since the pandemic forced people to spend more time at home, more people decided to take out their instruments and make music, since that was one of the things they could do at home. Now, there is obviously quite a bit of software which you can use if you play a guitar. Most of that is commercial and available for Windows. If you take a look at the Linux landscape, things become pretty narrow. There's basically Rack, which is discontinued. The last release was in November 2010, so almost 12 years ago. Then there's Guitarix, which is kind of a reference project for Faust, and that's basically it. And then there are plugin suites like Kaf, which I think is really great, but it's not really for guitar. It's mostly for mastering and generally more subtle modifications. So GoDSP Guitar is already kinda a unique piece of software on Linux, just because there really isn't too much audio software for Linux in general. But there's more that sets it apart from any other audio software or guitar plugins in general. First, it's truly cross-platform. It runs on Windows with i686 and x86-64. It runs on Linux with AArch64, ARM, and x86-64, and people have told me that it even compiles and runs on Mac, though we do not provide binaries for that platform. It is licensed under a permissive license, the Apache License 2.0. It is multi-channel and multi-instrument. With multi-instrument, I mean that a lot of stuff that it does is not necessarily tied to guitars. For example, it has a fully chromatic instrument tuner. It has modulation effects, filters, speaker simulation, compressors, and these things are really generic and not really specific for guitar. Multi-channel, on the other hand, means that it has multiple inputs and outputs. It can process many signals and many instruments at once, and they can be independent or interact with each other. This is a different paradigm than most audio plugins have. You run a single instance of GoDSP Guitar on your machine, which will internally multi-thread and process many instruments at once. And this allows for a different level of interaction between them as well. It's written in modern, high-level programming languages. In particular, we use Go for the signal processing and JavaScript for the UI. Using high-level languages gives us portability across operating systems and CPU architectures and increases readability and maintainability of our code. And these are widely used general-purpose languages. We do not use domain-specific languages. And we also have very few dependencies. There's no Zeta Convolver, Zeta Resample, FFTW, lib sound file, nothing of that sort. Of course, using high-level languages, we give up some of the control and are somewhat at the mercy of the compiler producing efficient code. There are no guarantees, especially across compiler versions. People have criticized us for that, and they're basically right. But the alternative is maintaining separate low-level code for every platform, which would lead to a lot of duplication and be hard to keep in sync. Also, low-level code is harder to understand and therefore also harder to maintain. So that was the choice we had to make. And the audio API that we use is Jack, which allows us to send and receive audio streams to and from both audio hardware and other applications. The software follows the Unix philosophy that application logic and user interface are separate. When it is started, it runs headless in the background and listens on a network socket over which it can be controlled. And when you connect to that socket with your web browser, it will display a modern web-based UI with touchscreen support. And of course, this will work over the network and also over Wi-Fi, so you could have your signal processing system backstage and then connect your tablet from stage and control your processing. It has two modes: a real-time mode where it uses Jack for actual hardware I/O, and a batch processing mode where it processes files in RIFWave RF64 format from the European Broadcasting Union EBU, or BW64, or Broadcasting Wave 64-bit format from the International Telecommunications Union, or ITU. And of course, the batch mode is also nice for debugging, since you cannot stop a real-time thread at a breakpoint. Most importantly, and this is perhaps one of the greatest differences from other audio software, it is based on a circuit simulation. In fact, this was created as a circuit simulation to aid in designing my own pedals. And then I thought, wait, this is so sick. Perhaps I can get this fast enough to run in real time and turn it into an audio plugin, so to say. So this really came from an engineering problem, and then I made it fast and turned it into an effects processor. And of course, now it has wave shapers in some places and everything to make it fast. But because it came from that engineering standpoint and accuracy was always key, this is probably one of the most realistically sounding and behaving amp sims you can find, at least in the open source world. So now I'm going to get a bit technical and tell you how all of this works. And of course I can't tell you everything, since this is quite a complicated piece of software. But I'm going to give you an overview about two things, and then I'm going to dig into the actual implementation of another two things. And I'm not going to show code. The code is available for everyone to see, and it keeps changing. But I'm going to show some diagrams and formula instead and explain things that way. So this is how the signal flow works in GoDSP Guitar. On the top and on the bottom, you can see your audio interface. On the top, you have the input section, where you usually have preamps and then analog-digital converters digitizing the signal. Your audio interface will normally have multiple inputs and multiple outputs. In this example, I've shown 2 inputs, and one of them, the one on the left, which I've called Capture 1, because that's usually how your driver will call it, has an instrument preamplifier and has a guitar connected, and the one on the right, which I've called Capture 2, has a microphone connected. And if you've already seen some of my tutorials, you might be familiar with this setup, since that's what I actually use for demonstration purposes. And on my interface, the signal from the first input bleeds a bit into the second input, but not the other way around, so I tend to put the signal where I need better quality into the first input. Anyway, the signal arrives on the ports in 0 and in 1 of GoDSP Guitar, and the connection is done by jack. And then you have these chains in GoDSP Guitar in which there are units, and the first unit gets a signal fed from jack, or in this case the hardware input, processes it, and then it gets passed downstream to consecutive units. So the input of the second unit is the output of the first, and so on. Now, this doesn't work in a pipelined way since we want to keep latencies low, so the signal will actually arrive on the output within the same simulation step, but conceptually this is what happens. And then the signal leaves GoDSP Guitar through output ports called out 0 and out 1, with out 0 being the processed signal from in 0 and out 1 being the processed signal from in 1. And of course, the chains are completely independent, so you can put completely different units in each and you configure them differently. And then in GoDSP Guitar, you actually have more outputs, like an output for a metronome signal and 2 outputs for a stereo mixdown, which includes a simple room simulation. Now, considering control, this is what the architecture is. When you run GoDSP Guitar, it will start this DSP process that you see on the right, and the DSP process runs the entire simulation and can process multiple chains, one for each channel. And within each chain, there are potentially many units, and these units have a type, which describes what sort of unit it is, like is it a function generator or a noise gate or a preamplifier or a phaser. These units can be arranged within an arbitrary order, and they can also be bypassed, which you can see here on the left. And each unit has potentially many parameters, like, for example, the signal generator has a frequency parameter, which is of type numeric and has a range from 20 to 20,000 Hertz. So we can see the range here from 20 to 20,000, and the physical unit is Hertz. And then it also has a parameter called signal type, which is of type discrete. So it can only take on discrete values, and these are sine, square, triangle, sawtooth, and noise. And then it has further parameters for adjusting the signal level and mixing the generated signal with the input signal and so on. And below that, the preamplifier, for example, has a gain and a level parameter, which are both of type numeric and have the physical unit dB or decibels. And gain runs from minus 30 to plus 30 dB, while level runs from minus 60 dB to 0 dB. And then there are global units like metronome, spatializer, level meter, chromatic tuner, and so on. Now, this DSP process runs in the background on your system, and it listens on a TLS socket for a control process to connect. And when this control process is a browser, the DSP process will deliver some JavaScript code to it, which provides the actual client or UI, which then connects back to the DSP process via TLS, and then the client or control process and the DSP process communicate back and forth by sending JSON-encoded messages over this TLS connection, like you can see here on the left. And the UI, which GoDSP Guitar provides by default, runs on mobile devices and has touchscreen support and everything. So this is really nice for controlling the software, and it frees us from having to use UI frameworks. But of course, you can create your own software, which establishes a TLS connection to the DSP process, and then you could, for example, translate MIDI commands into configuration changes or whatever. So this provides a lot of room for extension. So now I'm going to dive a bit into how certain units are implemented. And like I said, GoDSP-Guitar is basically a real-time circuit simulator. And on the first example, we're going to see what that means. So this is actually the circuit which GoDSP-Guitar simulates when you add a bandpass unit to your signal chain. Or rather, it is one of the potential circuits. In this diagram, you see a second-order active bandpass filter topology. It is an active filter since it contains active elements, these three amplifiers here. And it is a second-order filter since it contains two reactive elements, these two capacitors here. And what you can see here is that basically right after the input you have this first operational amplifier here which is configured as an impedance converter. It's a non-inverting amplifier with unity gain, and it serves to decouple the thing that comes right before in the signal chain, the thing that feeds into this input here, from the first RC circuit here. So I've already told it, this is an RC circuit. It's an RC high pass to be exact, which is driven by this impedance converter. Then we have another impedance converter, which ensures that this RC circuit is decoupled from whatever comes after. And then we have another RC circuit, this time an RC low pass, since the capacitor and the resistor are switched. And then we have another impedance converter, which ensures that this RC circuit is decoupled from everything that comes after it, and that's basically it. Now this first RC circuit is a high pass, so it will determine the lower limit frequency of the passband. Everything that is higher will be passed on, everything that's lower will be cut off. And the second order RC circuit is a low pass, so it will determine the upper limit frequency of the passband. Everything that is lower will be passed on, everything that is higher will be cut off. Now, like I said this is a second order active filter topology. You can configure the bandpass unit in GoDSP-Guitar to second, fourth, sixth, and eighth order filters, which means that there will just be more of these alternating RC high pass, RC low pass topologies after the other. And in case you're interested, these are the differential equations describing the behavior of the high pass filter. VC HPF is the voltage across the capacitor of the high pass filter, while Vin is the input voltage. And then you have VR HPF, the voltage across the resistor of the high-pass filter, which is the output of the high-pass filter. And then this basically drives the low-pass filter, which is described using this equation. The input of the low-pass filter is the output of the high-pass filter, so this plugs in here. And then for an RC low-pass filter, the output is the voltage across the capacitor. Now let's take a look at the power amplifier simulation. The power amplifier simulation makes heavy use of the fast Fourier transform, or FFT. What we do to create a model of a power amplifier is we first measure the step response of an actual power amplifier, which means we apply a step signal. So basically imagine we have 0 volts on the input of a physical amplifier. Then we make a sharp transition, and this has to be as sharp as possible. And then we have, for example, 1 volt of DC on the input of the power amplifier. And while we do this on the input, we measure what happens on the output and store this in a file. This is called the amplifier's step response. It's how the amplifier responds to a step signal on the input. Once we have measured this step response, we can calculate its derivative, which is the amplifier's impulse response. And to calculate this derivative, we can use the central difference method. The impulse response is how the amplifier would respond to an infinitely narrow impulse applied to its input. This impulse would have finite energy but infinite power since it has 0 duration. So this is a theoretical construct, and therefore we can't directly measure it, but we can measure the step response and then calculate this derivative. Once we have this impulse response, we can calculate the output signal from a given input signal by calculating the convolution between the input signal and the impulse response. And the convolution is this integral on the right. And this convolution can be calculated efficiently using the fast Fourier transform. the convolution of two functions is up to this constant 2 pi, the inverse Fourier transform of the product of the Fourier transforms of the functions. And the product that we use here to multiply these functions is the Hadamard product, or pointwise product, which means we multiply every complex amplitude in the Fourier domain evaluated at the same frequency. And then we apply the inverse Fourier transform, and then we have the convolution. However, convolution via the fast Fourier transform gives us circular convolution. But what we actually want to have is linear convolution, and to calculate that, we need a fast linear convolution algorithm. There are two of them. One is called overlap add, the other is called overlap save. And we have chosen overlap add here since this allows us to determine exactly how many output samples we want to generate, which is important since we run this in real time and we have to advance the simulation by an exact number of steps. The first FFT implementation that we used was the Cooley-Tukey algorithm from 1965, which is a recursive algorithm. The first optimization that we applied was that we calculated these Fourier coefficients or roots of unity in advance and stored them in an array or in a tree structure. And then we implemented another FFT algorithm, which is an iterative in-place algorithm, which saves us a lot of copying around the data and building up and tearing down the stacks. And our second optimization was one that we found in a white paper from Texas Instruments, and it allows us to calculate the FFT of a real-valued vector with 2 n elements using the FFT of a complex-valued vector with n elements and O of n post-processing operations. And finally, we have optimized our segmented convolution algorithms for the cases where the convolved signal is much longer or shorter than the filter kernel. Finally, here we have some sample signals which we display on a software scope. This is the output of our function generator, a sine wave with a frequency of 440 Hz. Now we put in an overdrive type preamplifier with 10 decibels of gain and symmetrical clipping, and we can see that the waveform gets compressed. Here we have a square signal with a frequency of 440 Hz from our function generator. And here we have that signal filtered through a second-order bandpass filter with a lower limit frequency of 300 Hz and an upper limit frequency of 3 kHz. And here we have a particular power amplifier topology, I don't know which one it is, where we put a 100 Hz sine signal through. And now we can provide some gain and see how this behaves. And finally, we see what happens when we increase the frequency from 100 Hz to 150 Hz. So where are we going to go from here? Well, there's actually a lot of stuff on our list, but realizing this is going to take a lot of time, especially since I don't have a lot of time to work on this project. First, and this is something that was requested by our users, we'd like to provide looper functionality. This will be available in real-time mode only, since it does not make sense for batch processing. It allows the user to record a loop and then add additional layers on top of it or overdub it. These individual layers can then be mixed, rearranged, time-shifted, and so on. One of the things that makes this quite complicated is that it needs exact synchronization with the metronome. Otherwise, if you start and stop the recording at an arbitrary point in time while the loop keeps playing, it will start shifting against the metronome beat, which is not what you would want. Also, the synchronization is necessary since you cannot start and stop with sample level accuracy. Input devices don't have arbitrary response times, and inter-process communication between the UI and the simulation takes time. And the audio is processed in blocks anyway, so we need something else to synchronize on. And finally, it is very complicated to do this on the UI level. The actual signal processing is more or less there, but the UI part really takes time to get right. The other major change we're currently working on is that we want to restructure our I/O architecture. First, we'd like to have more of a layered approach. We'd like to have a piece of code which handles the riff layer or a 64-bit variant of it, and then one which makes use of this riff layer and handles the WAV file format. Currently, there is code which handles both, and there's no separation into layers. Then we'd like to work directly on file descriptors. We'd like to read and write data on demand and no longer require it to be held in memory. This will enable us to process large files on memory-constrained systems, since we will only have in memory some section of the file we're currently working on. For data in memory, we'd also like to make use of these mechanisms. Therefore, we'd like to provide an abstraction which allows us to create a file in memory with which we can then interact as with any other open file descriptor. And all of this will require changes to the algorithms we use for sample rate conversion as well, since these currently assume that the entire file contents are in memory and can be randomly accessed. Finally, these changes will also allow us to enable benchmarking to determine the latency and throughput we can achieve on a particular system for a certain simulated circuit. Thank you.